Okay, here in Lesson 5a, we're going to continue our discussion of probability of two events called a compound probability, but this time we'll talk about AND cases. In the last lesson, we defined a compound event as one where we're finding the probability of some combination of two events, and we considered the OR case, the probability that an event A or an event B can happen to be considered success. We also saw that disjoint or mutually exclusive events are a special case which simplifies, modifies the OR probability formula. So in this lesson, we're going to explore the probability of event A and event B happening together. So A and B must both happen in order to consider the event successful, the outcome successful. And we'll see that there's also a special case which modifies the AND probability formula. Okay, so to begin, let's consider a survey taken of 100 high school students. We recorded the gender of each student and asked each one which of the following activities they preferred the most: reading a book, playing video games, or watching Netflix, and this table summarizes the responses. So, for example, this 12 here indicates that 12 girls selected video games as their favorite activity, and this 16 here represents that 16 boys selected watching Netflix as their favorite entertainment activity. Whenever we have a table of data like this, we should always add up the rows and columns to get the totals. Those are called the marginal values because they're in the margin of the table, but the actual data is actually the part inside the data table. But it is helpful to have the marginal values for probability calculations. Okay, so now we could find various probabilities, such as the probability that a student chosen at random from this group is a girl, or the probability that a student chosen at random likes to read a book, or that the probability that a student chosen at random is a girl and likes to read a book. Okay, so the probability that a chosen student is a girl is a simple probability. It's not a conditional probability because we're choosing from the entire sample space of all the students. So the probability of girl, right, the denominator, the bottom of the fraction, would be 100, which is the total of all of the students in the table. And then the numerator would be the part that reflects girl, right, which would be all of the girls in the table, which is 60. So it would be 60 out of 100, or 60%. Similarly, the probability that the chosen student likes to read a book would be out of the 100 students, the 22, regardless of girls or boys, the total of 22 students that like to read a book. And that's a simple probability because it's out of all of the 100 students, the entire sample space. Okay, so to find the probability that the chosen student is a girl and likes to read a book, we're still choosing a student out of all 100 students. So this is still a simple probability, not a conditional probability. And the bottom of the fraction would be 100, but this time we would have the more restricted number here, 18. To be included in girl and book, you have to like to read a book and also be a girl, right? So that would only be these 18 students, not the 60 girls and not the 22 people that liked a book, but the 18 that were both reading a book and being a girl. Right, so 18 out of 100 gives an 18% probability that a student is a girl and likes to read a book. By the way, the other way to write AND is to use the intersection symbol here. The reason why that's true is a little clearer. Now you can see that in the table, right? Because if reading a book is this row here, and being a girl is this column, then the 18 there is the intersection of those two, that row and that column. That's why the AND symbol is the intersection symbol, okay? All right, so we could also write probability of girl and book using the intersection symbol here, and that's the way that I'll typically write that in videos and in the exercises we do for examples. All right, so this number of students for girls and book, 18, is smaller than the number of girls, which was 60, and the number who like to read a book regardless of gender, that was 22, because to be in this group, the student must meet both requirements. So it makes sense that fewer students would meet this more stringent requirement. Right? For the OR case, we ended up adding probabilities. That was because it was easier for success to occur if there were two ways to be successful, so the probabilities needed to add so that we could get a larger probability than the individual event probabilities. But here for the AND case, it's harder for success to occur, so the AND probability should be lower than the probability of being a girl or the probability of liking a book. Right? When fractions are multiplied, the result is a smaller fraction, so that suggests we might try multiplying probabilities for the AND cases. So let's try that. We already know that the AND probability is definitely going to be 18 because we calculated it directly from the table. So over here on the side we've got the known good probabilities. Probability of a girl is 60%, probability that someone likes to read a book is 22%, and the probability that someone is a girl and likes to read a book is 18%. What we're investigating now is whether we could compute this 18% by multiplying the probabilities of the individual events that make that up, the probability of girl and the probability of liking a book. Okay, so let's test it. Let's compare the known good probability of girl and book, which is 18, to the probability of girl times the probability of book to see if multiplying works for AND cases. Okay, so the probability of girl was 60%, the probability of liking a book was 22, and when you multiply those two, you get 13.2%, not 18%, right? That doesn't work. So there has to be something going on here, and it turns out there is a catch in the AND case, just like there was a catch when we had the OR case. Okay, to investigate, let's take a closer look at just the girls column. Since we're choosing the girls column, it makes sense that one of the probabilities should be the probability of being a girl. So we're going to make that the first probability, the probability that the person is a girl, and that would be 60 out of 100, right? But the second probability, right, we shouldn't really just use probability of book, because if I use the 22 number over here, if I use that 22 number, that includes girls and boys, and we know we're supposed to be restricting ourselves to just the girls. So instead of considering the probability of book, really we should use a conditional probability. We should use the probability that someone likes a book given that they are a girl. That means we're going to stay within the girls column. So if we stay within the girls column and we say, okay, 18 students liked reading a book out of the 60, right, then that probability would be written this way. The probability that someone likes a book given that they're a girl. In other words, a conditional probability. So that suggests that while the first probability can be a simple probability, the probability of being a girl, the second probability really should be a conditional probability. It should be the probability of liking a book, but given the condition that you are a girl. Right? So let's redo that test to see if AND is multiplied, but this time we're going to use a conditional probability for the second probability. We're going to test, is it true that the probability of girl and book is the probability of girl times the probability of book given girl. Okay, so the probability of girl was 60%, right? 60 out of 100. And the probability of book given girl, the conditional probability, is 18, right, out of the 60 girls only. Right, so that'd be 18 out of 16 here, 18 out of 60. And when we multiply those two, the 60s cancel out, and we get 18 out of 100, which is 18%, which is what we know to be the correct probability for AND. So it does work. For AND cases, we do multiply, but the catch is that the second probability has to be a conditional probability. Okay. Here's another way to picture what's going on. The reason why I want to explain this is because this is actually the way I remember the formulas involved. Even though we're really just choosing a single student, we can imagine that the event, girl and book, each of those things, we can think of those as a separate choice. And imagine that we were making those choices in sequence, one after the other. So let's say, for example, we chose the gender, and then we chose the type of entertainment, right? We could make a tree diagram that shows the probabilities here, right? We could have girl or boy as the choice first, and then we could have book, games, or Netflix for the girl, and also book, games, and Netflix for the boy. If we were to label each branch with the probabilities, remember that the first branch here would contain simple probabilities, just the probability of all the students that they're girls, or the probability that they're boys. But the second probabilities all have to be conditional probabilities, right? This would be, for example, the probability that someone likes a book given that they're a girl. This one down here would be the probability that they like books given that they're a boy, right? Because we have to meet the condition to get to that portion of the tree. All right. So, and the end node probabilities are all the AND cases, right? To get to this spot in the tree, you have to be a girl and like a book. So this end probability out here would be the probability of being a girl and liking books. And this one down here would be the probability of being a boy and liking games. So if we just look at the top set of branches, it gives us an easy and visual way to remember the AND formula, and this is what I do. I picture a portion of a tree. So if I think of there being, I'm trying to find the probability of girl and book, then I think of those as two events, and I write girl, and then I write book, and I do a partial tree like this. Now, if you just look at the top of it, the first probability would be the probability of girl, and the second probability here would be the probability that we like that the person likes a book given that they're girl, and then the probability out here would be girl and book. That gives us an easy visual way to remember the AND formula. So let me build it for you, right? AND is multiply, we know that's true, right? Girl and book meaning those things happen. They both have to happen, so that means that we have to multiply these two probabilities, the probability of girl times the probability of book given girl, in order to get the and probability of girl and book. So that's a good way to remember and be able to rebuild the formula. Okay, so our decision, by the way, to list gender as the first choice in the tree, that was totally arbitrary. We could have instead decided to list the activity first, and if we did that, we would have book, games, and Netflix as the first choice, and then the gender, being girl or boy, would be the second choice. Here would be the probabilities all filled, and remember, you're watching a video, so you're welcome to pause this if you need to really take a look and see if you agree with this, right? But what I'm going to do is focus just on the top branch here to help me build the formula. Right? The first probability would be the probability of book, and the second probability would be the probability of being a girl given that you liked reading books, and then the last probability would be the probability of girl and book again. So that gives us another formula for girl and book. It could be probability of book times the probability of girl given book. Right? So the reason I wanted to go through that was to show you that there's actually two versions of this and formula. If I want to find the probability of someone being a girl and liking a book, I can take the probability of girl and multiply it by the probability of book given girl, or I could take the probability of book first and multiply it by the probability of girl given book. Both of those are valid formulas for the and probability. So, some people memorize that for probabilities and equals multiplication, and that idea is correct, but for it to work in all cases, we need to slightly modify that to account for the catch. It needs to be and equals multiplication, but one of the probabilities has to be a conditional probability. So, the probability of A and B is equal to the probability of A times the probability of B given that A happened. Or we could have written B first. The probability of B times the probability of A given that B happened. This is the true AND formula that works in all cases. Okay, in the next video we're going to talk about the special case here, which is called independent events, and that's a large enough topic that it warrants its own video.